Two spacecraft have crossed the edge of the solar system. Voyager 1 and Voyager 2 are the only machines that have ever done it. They went through 6 years apart, in different directions, and what their instruments measured broke almost every prediction we had made about what that boundary would look like. The termination shock was weaker than expected. The magnetic field refused to rotate. A region that no model had predicted appeared between the Sun's domain and the galaxies. The boundary was thicker, messier, more porous, and more alive than anyone had imagined. And the space on the other side was not what we expected either. The interstellar medium was hotter than it should have been, magnetically tangled with the Sun's own field, and disturbed by solar eruptions punching through the barrier from the inside. What Voyager measured at the edge changes how we understand the space that has been protecting every living thing on Earth since life began. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. Now, settle in. Get yourself comfortable. Let's begin. The space between the stars is not safe. Radiation that has been crossing the galaxy for millions of years is streaming toward the solar system right now, from every direction, at nearly the speed of light. It has always been there. It will always be there. And something has been standing between that radiation and the Earth for 4.5 billion years. That something is not a wall. It is not a fixed barrier built into the structure of space. It is something the sun itself creates, continuously. It is invisible. It emits no light. No telescope can photograph its edges. Every planet, every asteroid, every comet you have ever heard of fits inside it the way furniture fits inside a house. And for most of human history, nobody knew it existed. It is called the heliosphere. And to understand how it works, you first have to understand something most people never consider. The sun is not simply sitting there, quietly glowing, radiating warmth and light across the void. It is exploding, continuously. Every second of every day, the sun hurls roughly 1 million tons of material into space. Not light, not heat, actual physical matter. Protons, electrons, helium nuclei, trace heavier ions, all of them laced with tangled fragments of the sun's own magnetic field. This furious stream of charged particles races outward from the sun's upper atmosphere in every direction simultaneously, reaching speeds between 300 and 800 kilometers per second, depending on where it originates and the conditions on the solar surface at that moment. At its average pace, this stream covers the distance from Earth to the sun in under 5 days. Scientists call it the solar wind, and the name is dangerously misleading. Wind suggests something gentle, something that rustles leaves, a breeze that cools your face. The solar wind is a supersonic plasma torrent, moving faster than any bullet ever fired, faster than any missile ever built, faster than any object human engineers have ever launched from the surface of the Earth. The sun has been generating this wind for roughly 4.5 billion years. It began blowing when the sun first ignited, before the first single-celled organism appeared on this planet, before the oceans condensed from steam, before the Earth's crust had fully cooled, and it has not stopped for a single second since. Every moment, the sun loses mass to this outpouring, not enough to notice on human timescales. Over its entire lifetime, the sun has shed roughly a fraction of Jupiter's mass through the solar wind alone, and it still retains more than 99.9% of its original material. But the cumulative effect of that continuous outflow across billions of miles and billions of years is staggering, because the solar wind does not simply vanish into emptiness, it fills space. Starting at the sun's corona, the searing outer atmosphere where temperatures exceed 1 million degrees, the wind rushes outward past Mercury, past Venus, past Earth and Mars. It pushes through the asteroid belt. It sweeps past Jupiter, past Saturn, past Uranus and past Neptune. Beyond Neptune it keeps going, flying through the Kuiper belt, past the orbits of distant icy worlds like Pluto and Eris. All of this expanding material carries the sun's magnetic field with it, stretching those field lines outward like threads being pulled endlessly from a spool. The wind thins as it spreads, its density dropping with the square of the distance, but it does not disappear. Even at 100 times Earth's distance from the sun, the solar wind is still there. weaker, cooler, more diffuse, but present, still blowing, still carrying the sun's magnetic signature. And because the sun rotates, completing one full turn roughly every 27 days at its equator, the magnetic field embedded in the outflowing wind does not travel in straight lines. It curves. Imagine standing in a yard holding a garden hose, spinning slowly in place while the water sprays outward. The water leaves the nozzle pointing straight, but because you are turning, the overall pattern traces out a spiral across the ground. The sun does the same thing with its magnetic field. The result is a vast, elegant spiral structure winding outward through the entire solar system, named the Parker Spiral after the astrophysicist Eugene Parker, who predicted it in 1958, years before any spacecraft existed to confirm it. This rotating, spiraling, magnetically threaded wind pushes outward through interplanetary space, and as it does, it inflates something extraordinary. It inflates a bubble, not a soap bubble, not something fragile or thin-walled, a magnetic bubble of plasma larger than anything else the sun creates, larger than any planet's orbit, larger than the Kuiper belt. This bubble is the heliosphere. It is the region of space where the sun's particles and magnetic field dominate the local environment, where the solar wind defines the rules. Inside the heliosphere, you are inside the sun's domain. The particles around you came from our star. The magnetic field threading through the vacuum was born on the solar surface. Outside the heliosphere, the galaxy takes over. Different particles, born in supernova explosions millions of years ago. Different magnetic fields, shaped by the rotation of the Milky Way itself. Different plasma, colder, denser, with a completely separate origin story. The heliosphere is where one regime ends and the other begins. It is immense. At its nearest boundary, the innermost edge of the transition zone where the solar wind begins to falter, the heliosphere extends roughly 80 to 100 astronomical units from the sun in various directions. 1 astronomical unit is the distance from the Earth to the sun, approximately 93 million miles. So the nearest edge of the heliosphere's boundary region sits roughly 3 times farther from the sun than the most distant planet. The heliosphere dwarfs the planetary solar system the way a city dwarfs a single house, and the outer edge, the final surface where the solar wind is brought to a complete halt, lies even farther out still. But here is what makes the heliosphere genuinely important beyond the scale. It is not just an interesting structure. It is not just a feature for diagrams and textbooks. The heliosphere is a shield, and what it shields us from is something that would, in its absence, make the Earth a profoundly different and more dangerous world. The galaxy is not empty between the stars. The interstellar void is filled with a thin but relentless rain of subatomic projectiles called galactic cosmic rays. These are not gentle. They are protons, helium nuclei, and heavier atomic fragments accelerated to enormous fractions of the speed of light by the most violent events the universe produces: supernova explosions, colliding neutron stars, the accretion disks of black holes. Some individual galactic cosmic ray particles carry the kinetic energy of a professionally thrown baseball, compressed into a single nucleus smaller than an atom. When these particles strike the atmosphere of a planet, they shatter air molecules and generate cascading showers of secondary radiation that penetrate deep into the surface. On Earth, our atmosphere and magnetic field provide significant local protection, but even with both layers of defense, galactic cosmic rays remain the dominant source of natural radiation exposure for anyone who flies at high altitude, and they represent the single greatest health threat to astronauts venturing beyond low Earth orbit. Without the heliosphere, the cosmic ray flux reaching Earth would be substantially higher. The sun's magnetic bubble deflects, slows, and scatters a large fraction of incoming galactic cosmic rays before they ever reach the inner solar system. The effect is not theoretical, it is measured. Scientists have tracked how cosmic ray intensity at Earth's surface rises and falls in a clear rhythm tied to the 11-year solar activity cycle. When the sun is active and the solar wind is powerful, the heliosphere inflates to its maximum extent, and fewer cosmic rays penetrate to Earth's orbit. When the sun is quiet and the wind weakens, the heliosphere contracts, and more cosmic rays slip through the thinning defenses. Decades of continuous monitoring by ground-based neutron detectors and orbiting spacecraft have confirmed this pattern beyond any doubt. The Sun's output directly controls how much galactic radiation bathes the inner solar system. The cosmic ray rhythm is not just a measurement artifact. It reflects a physical change in the heliosphere itself. When the Sun is active, producing more sunspots, more flares, and a faster, denser solar wind, the increased outward pressure pushes the heliosphere's boundaries farther from the Sun. The termination shock, the heliosheath, and the heliopause all expand outward, inflating the bubble to its maximum extent. The thicker, more pressurized bubble deflects more cosmic rays. When the Sun enters the quiet phase of its cycle, with fewer sunspots and a weaker wind, the outward pressure drops. The interstellar medium, pressing inward with roughly constant force, squeezes the bubble back. The boundaries contract inward toward the Sun. The heliosphere shrinks, and more cosmic rays slip through the thinner, weaker defenses. This means the heliosphere is not static. It pulses, it breathes. Over the course of each 11-year solar cycle, the entire boundary structure expands and contracts by several astronomical units in each direction. The termination shock might sit at 95 astronomical units during solar maximum and pull back to 85 astronomical units during solar minimum. The heliopause shifts by comparable margins, though the exact magnitude depends on the direction from the Sun and the strength of the particular cycle. The heliosphere has been doing this for as long as the Sun has maintained a magnetic cycle, roughly 4 billion years, expanding and contracting in a slow rhythm that no one on Earth could detect until spacecraft ventured far enough outward to measure the boundary zones directly. This breathing has consequences that reach all the way back to Earth. When the heliosphere contracts during solar minimum, the inner solar system loses some of its shielding. Cosmic ray intensity at Earth's surface increases measurably, then decreases again as the next solar maximum reinflates the bubble. The effect is small enough that it poses no immediate danger to life on the ground, but it is large enough to matter for astronauts in orbit, for sensitive electronics aboard satellites, and for the chemistry of the upper atmosphere. Over geological timescales, more dramatic fluctuations in the Sun's wind strength, driven perhaps by long-term changes in solar magnetic activity or by the Sun's passage through denser regions of the interstellar medium, could compress the heliosphere far more severely, exposing the inner planets to cosmic ray levels substantially higher than anything measured in the modern era. The shield is real, but it is not rigid. It has never been rigid. It has always been breathing, expanding and contracting with the Sun's magnetic heartbeat, and the boundaries it creates are not fixed landmarks in space. They are living surfaces that move, respond, and shift with every change in the Sun's output. Any spacecraft attempting to cross those boundaries would not be crossing a stationary wall. It would be chasing a moving target. The implication is extraordinary. The Sun is not merely providing light and warmth. It is actively sheltering the entire planetary system inside a magnetic cocoon that blocks a significant fraction of the most dangerous radiation the galaxy produces. Every living thing on Earth exists in part because the Sun generates a wind fierce enough to hold the galaxy back. The planets do not orbit inside empty space. The WWWW, they orbit inside a protective enclosure that most people have never heard of, and until the middle of the 20th century, no scientist on Earth fully grasped that this enclosure existed. The existence of the solar wind was proposed theoretically by Eugene Parker in 1958, and the idea was so controversial that 2 out of 3 peer reviewers rejected his paper. Many physicists believed the space between planets was a static vacuum, not a dynamic outflow. The debate was settled in 1962 when the Mariner 2 spacecraft, on its way to Venus, directly detected a continuous stream of charged particles flowing outward from the Sun. The particles were there, blowing at the speeds and densities Parker had predicted. The interplanetary medium was not empty. The Sun was exhaling. But detecting the solar wind near Earth and understanding what it does at the outermost edges of the solar system are completely different problems. Near Earth, the wind is fast, relatively dense, and straightforward to measure. As it expands outward across billions of miles, it thins. Its density weakens. Its pressure fades. By the time the solar wind passes Jupiter, it has already declined significantly. By Neptune, it is a whisper of what it was near Earth. And beyond Neptune, it continues stretching, thinning, carrying less and less pressure against the interstellar medium pressing inward from every direction. This creates a question that dominated an entire generation of heliophysics. If the solar wind weakens with distance, where does it finally lose? Where does the outward pressure of the sun's particles become too feeble to push back against the inward pressure of the galaxy? Where is the edge of the bubble? For decades, the answer was entirely theoretical. Scientists built computer models, they calculated pressures, they estimated the density of the local interstellar medium. They argued at conferences about whether the boundary sat at 50 astronomical units or 200, but nobody actually knew because nobody had ever sent instruments there. The heliosphere's edge was too far away, too faint, and too invisible to study remotely. The only way to find it was to fly a spacecraft outward for decades and wait. Those spacecraft were never designed to find the heliosphere's boundary. They were designed to visit planets. In the early 1970s, an aerospace engineer named Gary Flandreau at the Jet Propulsion Laboratory discovered something remarkable about the alignment of the outer planets. Jupiter, Saturn, Uranus, and Neptune were approaching a geometric configuration that occurs only once every 175 years. A spacecraft launched at precisely the right moment could use the gravity of each planet to fling itself to the next, visiting all four gas giants in a single grand sweep. The concept became known as the Grand Tour. It was a once-in-2 centuries window, and missing it would mean waiting until the 22nd century for another chance. NASA built 2 spacecraft to seize it. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed 16 days later, on September 5th, on a faster trajectory that would carry it to Jupiter ahead of its twin. Both spacecraft were identical in design, each weighing roughly 815 kilograms. Each carried 10 scientific instruments including cameras, magnetometers, plasma detectors, cosmic ray telescopes, and ultraviolet spectrometers. Each was powered by 3 radioisotope thermoelectric generators that converted the decay heat of plutonium-238 into electricity. There were no solar panels. The mission planners knew these spacecraft would travel too far from the sun for sunlight to provide useful power. Voyager 1 reached Jupiter in March of 1979, returning images of the Great Red Spot, the volcanic eruptions on Io, and the cracked ice surface of Europa that hinted at an ocean beneath. It used Jupiter's gravity to slingshot towards Saturn, arriving in November 1980. There it photographed the intricate structure of the rings, discovered unexpected braiding and spoke patterns, and made a close pass of the moon Titan, whose thick orange atmosphere had fascinated planetary scientists for decades. That Titan flyby was the critical fork in the road. It bent Voyager 1's trajectory sharply upward, out of the plane of the planets. There would be no visit to Uranus, no visit to Neptune. Voyager 1 was heading north, climbing away from the ecliptic, on a one-way path into the outer darkness. Voyager 2 took a different road. It visited Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989, becoming the only spacecraft in history to visit the 2 outermost ice giants. Each flyby revealed worlds more alien than anyone had imagined. Geysers of nitrogen erupting from the frozen surface of Triton, a magnetic field on Uranus tilted 60 degrees from the planet's rotation axis, winds on Neptune shrieking at over 1,000 miles per hour, the fastest measured on any planet. After Neptune, Voyager 2 also turned outward, heading south and away, below the plane of the planets toward the emptiness beyond. By the early 1990s, both Voyagers had completed their planetary missions. The cameras were powered down. Voyager 1 captured one final backward glance in February 1990. The image known as the pale blue dot, a photograph of Earth from nearly 4 billion miles away, reduced to a fraction of a single pixel caught in a beam of scattered sunlight. After that picture, the cameras were turned off permanently. There was nothing ahead to photograph, only blackness. But the missions did not end. NASA redesignated them as the Voyager Interstellar Mission. The spacecraft were no longer planetary explorers, they were boundary hunters. Their remaining instruments, the magnetometers, the plasma detectors, the cosmic ray counters, the charged particle experiments, were ideally suited for a different kind of science. Instead of studying worlds, they would study the medium itself, the invisible ocean of particles and magnetic fields that fills the space between the planets and, somewhere far ahead, gives way to the very different ocean between the stars. Year after year, the Voyagers pushed deeper into the outer solar system. The signals grew fainter, the distances grew larger, the power from the plutonium generators declined steadily, losing roughly 4 watts each year to the slow, irreversible decay of the fuel. Engineers at the Jet Propulsion Laboratory began shutting down instruments and switching off heaters to conserve electricity, making painful decisions about which measurements to preserve and which to sacrifice. Every watt mattered. Every choice was permanent. You cannot send a technician to a spacecraft moving at 17 kilometers per second away from the Sun. Through the late 1990s and into the 2000s, the Voyagers sailed beyond the orbits of the most distant known objects in the solar system. They crossed the Kuiper Belt. They left behind the realm of known comets and icy dwarf planets. And all the while, their instruments quietly monitored the solar wind surrounding them. Speed, density, temperature, magnetic field strength and direction. Scientists on Earth watched every data point, year after year, looking for the first signs that the solar wind was beginning to change. And it was changing. Slowly, subtly, the solar wind measured by Voyager 1 began to decelerate, not in a sudden drop, not in a dramatic event, but a persistent, gradual decline in the outward velocity of the flowing plasma. The wind was still supersonic, still carrying the Sun's magnetic field, still blowing outward. But it was meeting resistance. Something ahead of Voyager, something invisible and vast, was pushing back against the Sun's exhale. That something was the interstellar medium, the thin, cold plasma that occupies the space between the stars in our arm of the Milky Way. This material is not empty. It contains roughly 1/10 of a particle per cubic centimetre on average, mostly hydrogen and helium, threaded with a weak but pervasive magnetic field generated by the collective motions of the galaxy. By human laboratory standards, it is a vacuum more perfect than anything we can create. By cosmic standards, it is a substance, a medium, a presence with real pressure, and that pressure pushes inward against the heliosphere on every side. The heliosphere is not a sphere. The name misleads. The Sun does not sit stationary at the centre of a perfectly round bubble. It moves through the local interstellar medium at roughly 26 kilometers per second, dragging its planets and its magnetic cocoon along. This motion compresses the heliosphere on its leading side and stretches it behind. The way a boat moving through water creates a compressed bow wave in front and a long, trailing wake behind. The leading edge, the nose of the heliosphere, faces toward the constellation Ophiuchus. On that side, the interstellar medium rams against the oncoming bubble, compressing the boundary closer to the Sun. On the trailing side, the heliosphere stretches into a long tail extending hundreds or possibly thousands of astronomical units downwind. The Sun is not resting calmly inside a tidy enclosure. It is ploughing through the galaxy, dragging an elongated, asymmetric wake of magnetized solar plasma behind it. The interaction between the outgoing solar wind and the incoming interstellar medium is not a clean handoff. It is a collision, a permanent slow-motion collision between two magnetized plasmas with different origins, different temperatures, different compositions, and different magnetic orientations. The solar wind pushes out. The interstellar medium pushes in. Where they meet, neither can simply pass through the other because magnetized plasmas resist mixing. They compress, they heat, they generate turbulence, they build boundaries, and those boundaries are what define the true edge of the heliosphere. Scientists predicted this collision would produce not one boundary, but at least 3 distinct transition zones stacked atop one another. The first zone would be the termination shock, the abrupt surface where the solar wind drops from supersonic to subsonic speed, like a jet aircraft decelerating through the sound barrier. Beyond the termination shock would be the heliosheath, a thick, hot, turbulent region of slowed and compressed solar wind that has been heated by the collision but has not yet been extinguished. And beyond the heliosheath would be the heliopause, the final surface where the outward pressure of the Sun's wind balances the inward pressure of the interstellar medium. Beyond the heliopause, the sun's particles would be gone. The galaxy would begin. 3 boundaries, 3 transitions. Not a single clean line drawn across space, but a complex, layered, turbulent frontier stretching across billions of miles. The models predicted it. The mathematics demanded it. But no one knew whether the real edge would match those predictions. No one knew how thick the transition zones would be. No one knew what the instruments would record at each crossing. And no one knew whether the Voyagers would survive long enough to reach even the first wall. By the early 2000s, Voyager 1 was approaching 90 astronomical units from the Sun. It had been travelling for 27 years. Its plutonium fuel had degraded measurably. Several instruments had already been turned off. The data transmission rate had been reduced to a thin trickle. The signal arriving at the deep space antennas on Earth carried less power than a refrigerator light bulb as seen from the distance of the Moon. Engineers calculated that the spacecraft might have roughly 2 more decades of useful life remaining before the electrical output would drop below the minimum needed to operate even a single instrument and a single transmitter, simultaneously. Somewhere ahead, in the darkness beyond the farthest known planet, the sun's wind was running into something it could not push past. The plasma was slowing, the pressure was building. A boundary that had existed for billions of years, long before any human looked up at the sky, was waiting in the blackness. Voyager 1 was closing in. And what its instruments would measure at that boundary, in the violent collision zone between our star and the galaxy, would overturn decades of careful predictions and reveal that the edge of the sun's domain is stranger, messier, and more layered than anyone had dared to imagine. The solar wind cannot blow forever. Voyager was about to find out where it stops. The first wall came on December 16, 2004. Voyager 1 had been travelling for 27 years. It was 94 astronomical units from the Sun, roughly 8.5 billion miles, more than 3 times the distance to Neptune. For months, the spacecraft's instruments had been recording precursor signals, brief surges in energetic particle counts, fluctuations in the magnetic field, hints that something enormous lay directly ahead. Then, within the span of a single day, everything changed at once. The magnetic field strength tripled, low-energy proton counts spiked upward, the character of the plasma surrounding the spacecraft shifted from fast and thin to slow and dense. Voyager 1 had crossed the termination shock, the innermost boundary of the heliosphere's edge, and what it encountered was not what the models had predicted. The termination shock is the surface where the solar wind, after racing outward for billions of miles, finally meets enough resistance from the interstellar medium that it can no longer maintain supersonic speed. Think of a river flowing fast and straight through a narrow canyon. When the canyon suddenly opens into a wide basin, the water does not gradually ease to a halt. It crashes into itself. The flow jams, compresses, heats up and churns as the fast-moving current is forced to decelerate. The solar wind does the same thing at the termination shock. It arrives supersonic, it leaves subsonic, and the transition generates a standing shock wave that wraps around the entire heliosphere like an invisible membrane billions of miles across. Scientists had spent decades predicting what Voyager would find at this shock. Most models expected a strong, well-defined boundary, a dramatic slam of fast wind hitting a hard wall of interstellar pressure. The reality was subtler and stranger. The shock Voyager 1 crossed was weak. The velocity jump ratio, the factor by which the solar wind speed dropped across the boundary, came in at roughly 2.6. Models had predicted values closer to 4. The shock existed, but it was gentler than expected, as if the solar wind had already been gradually bleeding energy before reaching the official boundary. Even more puzzling was what did not happen. For years, theorists had predicted that a specific population of particles, called anomalous cosmic rays, thought to be accelerated by the termination shock itself, would reach their peak intensity exactly at the shock front. These particles were supposed to be the shock's signature product. Voyager 1 found the shock, but the expected particle peak was not there. The termination shock was not doing what it was supposed to do, at least not at this particular spot on its vast, curved surface. The full implications of that missing peak would only become clear as Voyager spent years pushing deeper into the region beyond. There was another problem. The termination shock was not staying still. In the months before the crossing, Voyager 1's instruments detected signs that the shock was moving. The boundary had been pushed outward during years of strong solar wind pressure, reaching a maximum distance in mid-2004. Then, as solar wind pressure declined, the shock began retreating inward toward the Sun. Voyager 1 did not fly through a stationary wall. The wall came back and swept over the spacecraft as it contracted. The boundary was alive, breathing in and out with the rhythms of the solar cycle, and Voyager happened to cross it during an inward contraction. This single observation carried enormous implications. The termination shock is not a fixed landmark. It is a dynamic, fluctuating surface that responds to changes in solar activity across timescales of months to years. When the Sun flares and the wind strengthens, the shock pushes outward. When the Sun quiets, the shock pulls inward. The boundary Voyager 1 crossed on December 16th might have been in a completely different location 6 months earlier or 6 months later. Mapping the edge of the heliosphere from a single crossing point is like trying to map a coastline from one footprint in the sand while the tide is moving. 3 years later, the second footprint arrived. Voyager 2 crossed the termination shock in late August of 2007 at a distance of approximately 84 astronomical units from the Sun. It was travelling in a different direction, heading south rather than north, separated from Voyager 1 by roughly 110 astronomical units and 45 degrees of longitude around the heliosphere, and the distance was wrong. Or rather, the distance was surprising. Voyager 1 had crossed at 94 astronomical units. Voyager 2 crossed 10 astronomical units, closer to the Sun, a gap of nearly 1 billion miles between two measurements of supposedly the same boundary. This asymmetry confirmed what theorists had suspected, but could not prove with a single data point. The termination shock is not a perfect sphere centered on the Sun. It is lopsided. The interstellar magnetic field, pressing against the heliosphere from outside, distorts the shape of the boundary, compressing it more on one side than the other. Voyager 2, heading through the southern hemisphere of the heliosphere, encountered the shock closer in because the interstellar field pushes harder in that direction. The heliosphere is not symmetrically inflated. It is squeezed and warped by the galaxy's magnetic grip. Voyager 2 also carried a critical advantage that its twin lacked. Its plasma science instrument was still functioning. On Voyager 1, this instrument had failed in 1980, shortly after the Saturn flyby. Without it, Voyager 1 could not directly measure the speed, density, or temperature of the solar wind plasma. Scientists had to infer these properties indirectly from magnetic field and energetic particle data, a process that introduced uncertainty and left gaps in the picture. Voyager 2's working plasma detector could measure the solar wind directly, providing clean numbers. Across the termination shock, Voyager 2 recorded the solar wind speed, dropping from roughly 400 kilometers per second to around 200 at the shock boundary, then falling further to approximately 130 kilometers per second deeper in the heliosheath beyond. The deceleration was real, measured, and precisely quantified for the first time in history. 2 spacecraft, 2 crossings, 2 different distances, 2 different hemispheres. The termination shock was confirmed to exist, confirmed to be asymmetric, confirmed to be weaker than expected, and confirmed to be dynamic. But the termination shock was only the first wall. Beyond it lay something far stranger. The heliosheath is the thick, turbulent middle layer of the heliosphere's boundary region, the zone between the termination shock and the heliopause. Once the solar wind crosses the termination shock and drops to subsonic speed, it does not simply vanish. It piles up, it compresses, it heats, and it begins flowing sideways, deflected away from the nose of the heliosphere and swept back along the flanks toward the heliotail, like water flowing around a stone in a stream. This region is chaotic. The slowed solar wind is hotter and denser than the fast wind inside the termination shock, and its magnetic field is crumpled and turbulent, twisted by the compression into tangled configurations that resist neat mathematical description. Voyager 1 entered the heliosheath on the day it crossed the termination shock in December of 2004. It would not emerge from the other side until August of 2012. The data that came back was bewildering. For nearly 8 years, from December of 2004 to August of 2012, Voyager 1 crawled through the heliosheath. The distance across that zone turned out to be roughly 28 astronomical units, more than twice the distance from the Sun to Neptune, yet Voyager crossed it at a pace of only 3.5 astronomical units per year. It was the slowest and strangest leg of the entire mission. Nothing in the heliosheath behaved the way the textbooks had described. The first surprise was the temperature. When the solar wind crosses the termination shock, the kinetic energy of its supersonic motion converts into thermal energy. The plasma heats up. Models predicted this heating, but they underestimated its magnitude. The proton temperature in the heliosheath measured by Voyager 2's plasma instrument, once it crossed in 2007, reached roughly 100,000 to 200,000 Kelvin, several times hotter than the solar wind inside the termination shock, which typically runs between 10,000 and 50,000 Kelvin. The heliosheath was not just a transition zone, it was a furnace where the sun's wind was being crushed, decelerated, and cooked by the pressure of the galaxy pressing inward from every side. The second surprise came from the anomalous cosmic rays. These particles, atoms of interstellar origin that have been ionized, picked up by the solar wind, and then accelerated to high energies, were supposed to reach their peak intensity at the termination shock itself. The shock was widely regarded as their accelerator, the engine that boosted them to the energies observed at Earth. But when Voyager 1 crossed the shock, anomalous cosmic ray intensities did not peak. They kept climbing steadily throughout the heliosheath, year after year, as if the acceleration process was distributed across a vast region, rather than concentrated at a single boundary. This single observation forced a major revision in theories of particle acceleration at the heliosphere's edge. The termination shock, it turned out, was not the dominant accelerator in Voyager 1's sector. The acceleration was happening elsewhere on the shock's enormous curved surface, or perhaps across the entire heliosheath through mechanisms the models had not fully incorporated. Third, the magnetic field in the heliosheath was tangled in ways that defied clean mathematical description. Inside the termination shock, the Parker spiral provides a relatively orderly framework. The field lines spiral outward in a predictable pattern, governed by the sun's rotation rate and the solar wind speed. In the heliosheath, that order collapsed. The magnetic field was compressed, folded, and crumpled by the deceleration of the plasma, creating a turbulent patchwork of field orientations that shifted on timescales of hours to days. Voyager's magnetometer recorded abrupt changes in field direction, sudden reversals, and intervals of almost eerily quiet field, followed by bursts of intense fluctuation. The heliosheath was magnetically chaotic, a region where the sun's field had been crumpled like a sheet of paper squeezed inside a fist. The solar wind in the heliosheath was not behaving as models had predicted. Its speed, already reduced to subsonic levels at the termination shock, continued to decline. By 2010, the radial component of the solar wind velocity measured by Voyager 1's low-energy charged particles instrument had dropped to essentially zero. The wind was no longer moving outward at all. It was flowing sideways, deflected by the pressure of the interstellar medium ahead. The sun's exhale, after travelling for billions of miles over billions of years, had finally been brought to a dead stop in the radial direction. Whatever outward push remained was being redirected along the boundary, channeled away from the nose toward the tail. Meanwhile, galactic cosmic ray counts were climbing steadily. Inside the termination shock, the heliosphere provides effective shielding against cosmic rays from the galaxy. In the heliosheath, that shielding was weakening. More and more galactic particles were leaking inward through the increasingly porous boundary. Voyager 1 was measuring the slow failure of the sun's protective barrier, watching the shield thin from the inside as the spacecraft pushed closer to the outer edge. Then, in the middle of 2012, something bizarre happened. Voyager 1 entered a transition zone that mission scientists had never anticipated. They called it the magnetic highway. In this region, the energetic particles from inside the heliosphere dropped away sharply, while galactic cosmic rays surged to near interstellar levels. Yet the magnetic field did not change direction. It still pointed the same way it had throughout the heliosheath, aligned with the sun's spiral field. Particles were escaping and entering freely along the magnetic field lines, as though someone had opened doors at both ends of a corridor, allowing traffic to flow in and out. But the corridor itself, the magnetic structure, remained anchored to the Sun. The magnetic highway persisted for roughly 3 months, counting from the first intermittent particle depletions in late May to the final crossing in late August. During that time, Voyager 1 occupied a region that did not fit any existing category. It was not the heliosheath, because heliospheric particles were largely absent. It was not interstellar space, because the magnetic field still carried the Sun's orientation. And it was not the heliopause itself, because the plasma density had not yet jumped to interstellar values. Scientists had no name for this zone, because no model had predicted its existence. Some researchers proposed that Voyager had entered a region where magnetic reconnection, the process by which field lines from different sources break and rejoin, had opened channels connecting the inside and outside of the heliosphere along specific field lines. Particles could stream freely through these channels, entering and exiting the bubble, while the bulk magnetic structure remained intact. The heliosphere was leaking, not catastrophically, not everywhere, but along specific magnetic corridors. The bubble was porous, allowing the galaxy's cosmic rays to flood in and the Sun's energetic particles to drain out simultaneously. This was the first direct evidence that the heliopause is not a sealed membrane. It has gaps, it has connections. The inside and outside communicate through magnetic topology in ways that static models which treat the boundary as a smooth, impermeable surface simply cannot reproduce. The magnetic highway demonstrated that the heliosphere's outer boundary is stitched together with magnetic threads that link the solar and interstellar domains, and that particles exploit these threads to cross the boundary long before the bulk plasma transition occurs. This was not supposed to happen. In every model of the heliopause, the magnetic field was expected to rotate dramatically as the spacecraft crossed from solar-dominated plasma into interstellar-dominated plasma. The Sun's magnetic field spirals outward in one orientation. The interstellar field points in a completely different direction. Crossing from one regime to the other should produce a clear, measurable swing in the field direction, the way a compass needle swings when you carry it past a strong magnet. The magnetic highway showed that particles knew the boundary was near, but the field itself was not cooperating. Then came August 25th, 2012. On that date, Voyager 1's cosmic ray subsystem recorded a final sharp surge in galactic cosmic ray intensity. Simultaneously, the energetic particles from the Sun, the heliospheric population that had been the spacecraft's constant companion for 35 years, dropped to the instrument's background noise level and stayed there. They were gone, vanished. The solar wind particles that had surrounded Voyager since launch day in 1977 had disappeared in a matter of hours. Galactic cosmic rays flooded in to replace them, reaching intensities roughly 40% higher than anything measured inside the heliosphere. By every particle measure, Voyager 1 had crossed the heliopause. It had left the Sun's bubble. It was in interstellar space, but NASA did not announce it, not for 13 months, because the magnetic field refused to rotate. The magnetometer aboard Voyager 1, operated by a team led by Leonard Berlar-Gar, recorded that the magnetic field strength increased at the crossing, exactly as expected. The field was stronger outside the heliopause than inside the heliosheath, but the direction of the field barely changed. It remained oriented in nearly the same direction as the solar magnetic field, with no significant swing toward the interstellar field direction that the IBEX spacecraft had independently estimated from energetic neutral atom observations. The most anticipated signature of the heliopause crossing, the one theorists had described for decades as the unmistakable marker, was the one that did not show up. This created a scientific crisis. Two instruments were telling contradictory stories. The particle detectors said Voyager 1 was in interstellar space. The magnetometer said maybe not. Some scientists proposed that Voyager had entered a new and unexpected region of the heliosphere, rather than crossing into the interstellar medium. Others argued the magnetic field measurement simply meant the boundary was more complicated than anyone had predicted. The debate paralyzed the announcement. The resolution came from an instrument that had been designed for a completely different purpose. The plasma wave subsystem, built to detect electric field oscillations in plasma, recorded a series of electron plasma oscillations in April of 2013, triggered by a solar eruption that had sent a pressure wave rippling outward through the heliosheath and into the interstellar medium months earlier. These oscillations revealed the local electron density surrounding Voyager 1. The density was roughly 40 times higher than anything ever measured inside the heliosphere. It matched the predicted density of the local interstellar medium. That measurement broke the deadlock. The density was interstellar. The particles were interstellar. The magnetic field direction was strange, but the plasma wave data provided the confirmation the particle instruments could not deliver alone. On September 12, 2013, more than a year after the actual crossing, NASA officially announced that Voyager 1 had entered interstellar space. The date of the crossing was fixed retroactively to August 25, 2012, based on the cosmic ray and particle data. Voyager 1 had become the first human-made object to leave the sun's bubble and directly sample the space between the stars. But one spacecraft crossing one boundary at one location could not answer the questions the magnetic field mystery had raised. Was the missing rotation a local fluke? Was it caused by the specific geometry where Voyager 1 happened to cross? Or was the heliopause fundamentally different from what theories described? 6 years later, the second crossing answered some of those questions and deepened others. Voyager 2 crossed the heliopause on November 5, 2018, at a distance of approximately 119 astronomical units from the Sun. It was travelling in a different direction than its twin, heading through the southern hemisphere of the heliosphere at roughly 31 degrees south heliographic latitude. The crossing distance was strikingly close to Voyager 1's, 122 astronomical units versus 119, a difference of only about 3 astronomical units across a boundary billions of miles wide, measured by two spacecraft crossing at different locations, in different directions, during opposite phases of the solar cycle. Scientists had expected the heliopause distance to vary significantly depending on where and when you crossed it. The near match between the two measurements remains only partially explained. Voyager 2's crossing was cleaner than its twins. The spacecraft carried a functioning plasma science instrument, the one that had failed on Voyager 1 back in 1980. This detector measured the solar wind plasma directly, and at the moment of crossing, the data was unambiguous. The sunward-pointing plasma cups, which had been registering continuous solar wind flow for 41 years, dropped to background noise levels on day 309 of 2018. The solar wind was gone. In its place, the sideways-pointing detector began registering a new population of particles, colder, denser plasma that had never originated at the Sun. These were the first direct measurements of interstellar plasma by any spacecraft in history. The temperature of that interstellar plasma was a surprise. Models and prior indirect observations had predicted that the very local interstellar medium near the heliopause would have a temperature between 15,000 and 30,000 Kelvin. Voyager 2 measured temperatures between 30,000 and 50,000 Kelvin. The interstellar gas was significantly hotter than expected, likely because the plasma is compressed and heated as it presses against the heliosphere. The space just outside the Sun's bubble is not cold and placid. It is warm and disturbed, influenced by the very boundary it is pushing against. Voyager 2 also discovered a feature that Voyager 1 had not seen. In the heliosheath, just inside the heliopause, Voyager 2 passed through a region of significantly enhanced magnetic field strength that scientists named the magnetic barrier. This zone, roughly a tenth of an astronomical unit thick, appeared to be a layer where the solar magnetic field piles up against the heliopause, compressed and intensified by the pressure of the interstellar medium just beyond. It acted like a buffer, a magnetic cushion between the solar and interstellar domains. Voyager 1 had not encountered a comparable magnetic barrier, suggesting that the structure of the heliopause boundary layer varies depending on where you cross it. The differences between the two crossings extended beyond the magnetic barrier. In the weeks leading up to its heliopause transit, Voyager 1 had passed through several brief episodes that scientists described as flux transfer events, short-lived incursions into regions where particle signatures momentarily resembled interstellar space, before reverting to heliosheath conditions. These episodes gave the impression that the heliopause was rippling, that the boundary surface was not fixed, but undulating back and forth across Voyager's trajectory, briefly immersing the spacecraft in interstellar plasma before sweeping past again. The crossing on August 25th was simply the final, permanent immersion after weeks of intermittent contact. Voyager 2 experienced nothing like that. Its crossing was abrupt and singular. The plasma cups registered solar wind one day and background noise the next. There were no precursor flux transfer events, no magnetic highway, no months of ambiguity. The heliosheath ended, the heliopause appeared, and interstellar space began, all within a span of roughly one day. Scientists interpreted the difference as evidence that the heliopause boundary layer is not uniform. In some sectors it is thick, rippled, and magnetically complex, allowing extended transition zones like the one Voyager 1 experienced. In other sectors it is thin, sharp, and decisive, as Voyager 2 observed. The heliopause may look completely different depending on the latitude, the longitude, the phase of the solar cycle, and the local configuration of the interstellar magnetic field pressing against it from outside. This variability presents a fundamental challenge to any single description of the heliosphere's edge. The boundary that Voyager 1 crossed and the boundary that Voyager 2 crossed were both the heliopause. They were both the surface where the solar wind yields to interstellar pressure, but they differed in thickness, in magnetic structure, in the presence or absence of a magnetic barrier, in the behavior of energetic particles during the approach, and in the sharpness of the final transition. Two measurements of the same boundary produced two substantially different portraits. And then there was the magnetic field direction. Again, at Voyager 2's heliopause crossing, scientists watched the magnetometer data with particular intensity. They knew what had happened at Voyager 1. They knew the field had not rotated. They needed to know whether the same thing would happen at a completely different crossing point. The result was decisive. The magnetic field did not rotate at Voyager 2 either. As at Voyager 1, the field strength increased at the boundary, but the direction remained nearly aligned with the solar magnetic field. There was no dramatic swing toward the interstellar orientation. The most predicted signature of the heliopause, the feature that textbooks and models had described for decades, failed to appear at both crossings, 6 years apart, in different hemispheres, during different solar conditions. Whatever was happening at the heliopause, it was not a simple, clean transition from one magnetic domain to another. The boundary was layered, gradual and porous, with magnetic field lines connecting the inside and outside of the heliosphere rather than separating them sharply. One researcher put it bluntly: nature had not read the theorists' papers and did not know it was supposed to change the magnetic field direction. The combined Voyager data painted a picture of the heliosphere's edge that was profoundly different from the one that had existed in textbooks. The termination shock was weaker and more dynamic than predicted. The heliosheath was thicker, hotter, and more complex. The heliopause was not a clean wall but a layered, porous, magnetically connected membrane that allowed particles to leak in and out, and whose structure differed depending on where you sampled it. The edge of the solar system was not a single line. It was a frontier, a transition zone tens of billions of miles thick, messy and turbulent, and alive with interactions between two vast plasma systems that refused to obey simple models. Voyager 1 and Voyager 2 had crossed the same fundamental boundary, confirmed each other's results, and between them measured the heliosphere's edge in ways no model had fully anticipated. They had proven that the Sun's domain has a definite outer limit, that the solar wind does stop, that a boundary exists where the Sun's influence yields to the galaxy's pressure. But they had also proven something else, something that unsettled the scientific community as much as it excited them. The space on the other side was not what anyone had expected. The interstellar medium just beyond the heliopause was hotter, more magnetically complex, and more entangled with the Sun's own field than any prediction had allowed. Voyager had crossed the edge, but the edge was not an ending. It was the beginning of a different kind of strangeness, one that would force scientists to reconsider not only where the solar system ends, but whether ending is even the right word for what happens at the boundary between a star and its galaxy. What the instruments found beyond the heliopause would challenge that question in ways that are still not fully resolved. Voyager 1 crossed the heliopause in August of 2012. The particles changed, the plasma density jumped, the cosmic ray counts surged. By every measure of the medium surrounding the spacecraft, it had left the Sun's bubble and entered interstellar space. The announcement, when it finally came in September of 2013, was treated as a culmination. The mission had done what it set out to do. It had reached the edge and crossed it, But crossing a boundary is not the same as understanding it, and in the years that followed, the instruments still functioning aboard Voyager 1 began sending back data that made the heliopause look less like a door the spacecraft had walked through, and more like a fog it had wandered into without reaching the other side. The magnetic field was the first and most persistent puzzle. The fact that the field direction did not rotate at the heliopause had delayed the crossing announcement by more than a year and had left a deep, unresolved question in the data. If Voyager 1 was truly in interstellar space, why did the magnetic field still point in roughly the same direction as the Sun's spiral field? Why had the interstellar magnetic field not asserted itself? The answer that emerged over the following years reframed the heliopause entirely. In 2015, astrophysicist Nathan Schwadron and colleagues at the University of New Hampshire published an analysis that proposed a strikingly physical explanation. The interstellar magnetic field does exist beyond the heliopause, and it does point in a different direction than the solar field. But right next to the heliopause, that interstellar field is not free to point wherever it wants. It is being deflected. The heliosphere, as it plows through the interstellar medium, forces the surrounding magnetic field to wrap around it. The interstellar field lines cannot cut through the heliopause because the two magnetized plasmas resist mixing. Instead, the field lines drape over the surface of the bubble, bending and stretching as they flow around the obstruction. Schwadron described it in a way that became the defining image of the phenomenon. If you think of the magnetic field as a rubber band stretched around a beach ball, the band does not point in its natural resting direction anywhere near the surface of the ball. It is distorted, pulled, redirected by the shape of the obstacle it is wrapped around. Only far from the ball, where the rubber band is no longer in contact with the surface, does it relax back to its undisturbed orientation. This meant that Voyager 1, even after crossing the heliopause, was still travelling through a region where the interstellar magnetic field had been bent out of shape by the Sun's bubble. The spacecraft had left the heliosphere, but it had not yet escaped the heliosphere's gravitational shadow on the surrounding field. It was moving through a disturbed region, an outer envelope of deflected interstellar magnetism that some scientists began calling the outer heliosheath, a zone that technically lies in interstellar space, but still carries the imprint of the Sun's presence. Schwadron's team made a prediction. If the magnetic field was being deflected by draping, then it should gradually rotate toward its true interstellar orientation as Voyager 1 moved farther from the heliopause. Degree by degree, year by year, the field direction should creep toward what the IBEX spacecraft had independently identified as the undisturbed interstellar magnetic field direction. The team predicted that by approximately 2025, if the rotation continued at its observed pace, Voyager 1 would finally measure a field direction matching the IBEX estimate. That would mark the spacecraft's arrival in pristine interstellar space, the region beyond the Sun's last magnetic fingerprint. 2025 came. The rotation had continued, but the prediction was not fully borne out. A paper published in the Astrophysical Journal in 2026, using Voyager 1 magnetometer data through mid-2025, confirmed that the magnetic field direction had indeed been rotating since the heliopause crossing. The normal component of the field had decreased significantly, and the overall orientation had shifted measurably toward the expected interstellar direction. The trend was real and ongoing, but the rotation had not yet converged on the IBEX predicted value. Voyager 1, now approximately 167 astronomical units from the Sun, and more than 45 astronomical units beyond the heliopause, was still measuring a field that bore traces of solar influence. The paper noted something else. After a large magnetic disturbance called Pressure Front 2 passed over the spacecraft around 2020, the turbulence in the magnetic field had quieted dramatically. Fluctuations dropped to near Gaussian levels, essentially indistinguishable from instrument noise. Some members of the research team suggested that Voyager 1 might have entered a new equilibrium region beyond the zone of active solar disturbance, but the continued deviation in field direction argued against declaring the spacecraft to be in pristine, undisturbed interstellar space. The Sun's magnetic shadow still reached it, faintly but measurably, even at this extraordinary distance. This finding carries a profound implication. The heliosphere does not end cleanly at the heliopause. The sun's influence bleeds outward beyond its own bubble, distorting the surrounding interstellar field for tens of astronomical units in every direction. The boundary between our star and the galaxy is not a wall, it is a gradient, a slow transition, a zone where the sun's dominance fades and the galaxy's dominance grows, but where the two overlap and intermingle across a region larger than the entire planetary solar system. Voyager was not the only thing reaching across that boundary. The sun itself was reaching across it. In the years following the heliopause crossing, Voyager 1 detected multiple pressure disturbances propagating through the interstellar plasma. These were not interstellar events, they were solar events. Massive eruptions on the sun, coronal mass ejections that hurled billions of tons of magnetized plasma into the heliosphere, generated pressure waves that traveled outward through the solar wind, crossed the heliosheath, slammed into the heliopause, and transmitted through the boundary into the interstellar medium on the other side. Like the thud of a drum beat passing through a wall into the next room, the sun's violent outbursts were punching through its own bubble and disturbing the galaxy beyond. Voyager 1's plasma wave subsystem detected these transmitted shocks as electron plasma oscillations, the same type of signal that had confirmed the heliopause crossing in 2013. Each time a solar-driven pressure wave arrived at Voyager 1's location in interstellar space, it excited oscillations in the local plasma that revealed the electron density at that point, and each successive measurement showed a density higher than the last. The interstellar plasma density was not uniform. It was increasing with distance from the heliopause, rising in steps as Voyager moved deeper into the interstellar medium. Between 2012 and 2020, Voyager 1 detected at least 3 major pressure events in the very local interstellar medium. Each one created measurable changes in the magnetic field strength, the plasma density, and the cosmic ray intensity at the spacecraft's location. Some events produced clear shock structures, abrupt jumps in field strength that propagated outward from the heliopause. Others appeared as smoother compression waves that built gradually and dissipated over weeks. The timing of these events revealed something remarkable about the connection between the sun and the space beyond its bubble. One of the clearest cases occurred in 2014, when a powerful coronal mass ejection left the sun, travelled outward through the heliosphere at roughly 700 kilometers per second, crossed the heliosheath where it decelerated significantly, struck the heliopause, and transmitted a pressure pulse into the interstellar medium on the far side. Voyager 1's plasma wave subsystem detected the resulting electron oscillations roughly 480 days after the original solar eruption. Nearly a year and a half of travel time, across more than 120 astronomical units of space, through 3 distinct plasma environments, and the disturbance still arrived with enough energy to excite measurable oscillations in the interstellar plasma. The sun had reached across its own boundary and physically disturbed the galaxy. That detection also provided a critical density measurement. The oscillation frequency is directly related to the electron density of the surrounding plasma. Each successive pressure event that Voyager 1 detected showed a slightly higher density than the last, consistent with the spacecraft moving outward through a density gradient in the very local interstellar medium. Between 2012 and 2020, the electron density measured at Voyager 1's position roughly doubled, rising from approximately 0.05 electrons per cubic centimeter near the heliopause to approximately 0.1 electrons per cubic centimeter farther out. This gradient was steeper than most models had predicted, and suggested that the interstellar plasma near the heliopause is compressed and piled up against the boundary, creating a dense layer that thins gradually with distance. The heliosphere, simply by existing, reshapes the galactic material surrounding it for tens of astronomical units in every direction. The interstellar medium near the sun was not the quiet, static environment that older models had described. It was agitated, stirred, influenced by the sun in ways that extended well beyond the heliopause boundary. Voyager 2, travelling through a different sector of the interstellar medium in the southern hemisphere, detected its own set of pressure events after crossing the heliopause in 2018. But the disturbances at Voyager 2's location looked different from those at Voyager 1. The magnetic field profiles were smoother, more wave-like, lacking the sharp shock fronts that Voyager 1 had measured. This difference may reflect the different locations of the two spacecraft, relative to the heliopause geometry, or it may indicate that the interstellar medium is not homogeneous, that conditions vary depending on where you sample them. A 2026 modelling study attempted to reconcile the two sets of observations and concluded that no single simulation could fully explain both. The interstellar medium near the heliopause remains only partially understood. The picture that emerges from over a decade of post-heliopause measurements is one of unexpected complexity. The very local interstellar medium, the region within roughly 50 astronomical units of the heliopause, is not pristine galactic space. It is a disturbed zone, heated and compressed by the heliosphere's presence, stirred by solar pressure waves, and magnetically entangled with the sun's field through draping effects that extend far beyond the nominal boundary. The heliopause marks the end of the solar wind, but it does not mark the end of the sun's reach. The sun's influence extends outward like smoke from a bonfire, drifting over a fence into a neighbour's yard. The fence is real, the property line is real, but the smoke does not respect it. This realization raised a deeper question about how well we can understand the heliosphere's structure from only two measurement points. Voyager 1 crossed in the northern hemisphere, Voyager 2 crossed in the south. Together, they sampled two locations on a boundary that wraps around the entire solar system in 3 dimensions. Trying to describe the full shape and behavior of the heliosphere from these two crossings is like trying to describe an entire ocean from 2 cups of water scooped from different beaches. The cups tell you the water is salty. They tell you the temperature at those 2 spots. They do not tell you the shape of the coastline, the depth of the basin, or whether a storm is building on the far side. For decades, the only tool available to complement the Voyager measurements was the Interstellar Boundary Explorer, IBEX, a small spacecraft launched in 2008 into Earth orbit. IBEX does not travel to the heliosphere's edge. It maps the boundary from the inside by detecting energetic neutral atoms, fast-moving particles created when solar wind ions in the heliosheath exchange charge with neutral interstellar atoms. These neutral particles, no longer bound by magnetic fields, fly inward in straight lines and can be captured by detectors near Earth. By mapping the directions and energies of incoming energetic neutral atoms across the entire sky, IBEX creates a crude image of the heliosphere's boundary region, a picture taken from the inside of the bubble looking outward at its walls. IBEX's most startling discovery was the ribbon. It appeared in IBEX's first all-sky maps, and it immediately became one of the most debated features in heliophysics. The ribbon was not a faint statistical trend extracted from noisy data. It was vivid, a bright, narrow arc of enhanced energetic neutral atom flux stretching roughly 300 degrees across the sky, cutting through constellations from one horizon of the heliosphere to the other. Its width was only about 20 degrees, making it a sharply defined feature against the broader, diffuse glow of the heliosheath. Within months of its discovery, the ribbon became the single most discussed observation in heliophysics. Over a dozen competing hypotheses were published in the first 2 years alone. Some scientists proposed that the ribbon was produced by a secondary population of energetic neutral atoms created in the outer heliosheath, the disturbed interstellar region just beyond the heliopause. In this scenario, neutral atoms from the heliosheath cross the heliopause, become ionized by the interstellar magnetic field, gyrate around interstellar field lines, and then recapture an electron to become neutral again. This second-generation neutral atom flies back inward and can be detected by IBEX. The process preferentially produces neutrals in directions where the interstellar magnetic field is perpendicular to the radial line of sight from Earth, because the gyrating ions spend more time in the plane perpendicular to the field. This geometric enhancement creates a ring on the sky, a ribbon, whose center corresponds to the direction of the interstellar magnetic field far from the heliosphere. Other researchers proposed alternative mechanisms involving instabilities at the heliopause, compressions in the heliosheath, or even reflections of solar wind particles off the interstellar field. The debate has narrowed over the years. The secondary neutral atom hypothesis remains the leading explanation, supported by simulations that reproduce the ribbon's width, position, and energy dependence. But observational confirmation has remained elusive because IBEX's angular resolution is too coarse to distinguish fine structural predictions that would separate the competing models. A paper published in the Astrophysical Journal in July of 2026 used the combined IBEX dataset of nearly 18 years, alongside early IMAP observations to refine estimates of the interstellar field, direction inferred from the ribbon center. The results showed that the magnetic field direction implied by the ribbon still does not match what Voyager 1 or Voyager 2 are measuring locally, reinforcing the interpretation that both spacecraft remain in magnetically draped regions influenced by the heliosphere, even though they have crossed the heliopause itself. The ribbon, in other words, is not just a curiosity in the energetic neutral atom maps. It is a compass. It points toward the magnetic field of the undisturbed galaxy, the field that exists far beyond the Sun's influence, the field that Voyager 1 has been slowly rotating toward since crossing the heliopause in 2012. This is the same direction that Schwadron's team used as the target for Voyager 1's slowly rotating magnetic field. The ribbon gave scientists an independent estimate of where the interstellar field should point when it is no longer being deflected by the heliosphere. That estimate remains the benchmark against which Voyager 1's ongoing measurements are compared, and the gap between the two, while shrinking, has not yet closed. But IBEX, for all its contributions, is limited. Its energetic neutral atom maps have coarse angular resolution and are averaged over long time periods. They reveal the heliosphere's gross structure, but cannot resolve fine details or rapid changes. The heliosphere is dynamic. It responds to the solar cycle. Its shape fluctuates, its boundaries move. IBEX can see the broad strokes, but the brushwork is blurred. That limitation is why the Interstellar Mapping and Acceleration Probe, IMAP, matters so much. IMAP launched on September 24, 2025, aboard a SpaceX Falcon 9 rocket from Kennedy Space Center. It reached the Sun-Earth Lone Point, approximately 1 million miles from Earth toward the Sun, on January 10, 2026, and began its primary science mission on February 1st. IMAP carries 10 scientific instruments, including 3 energetic neutral atom detectors with significantly higher resolution and sensitivity than IBEX. Where IBEX produced rough maps, IMAP will create detailed, time-resolved images of the heliosphere's boundaries, tracking how the termination shock and heliopause respond to solar activity in near real time. IMAP will also measure pickup ions, interstellar atoms that have been ionized by solar radiation and swept up by the solar wind. These particles carry direct information about the composition and density of the interstellar medium passing through the heliosphere. Combined with the energetic neutral atom maps, pickup ion measurements will provide a 3-dimensional picture of the heliosphere that no previous mission could achieve. The timing is deliberate. IMAP's primary mission covers 2 years, spanning a period of increasing solar activity as the Sun approaches its next solar maximum. This allows the mission to observe how the heliosphere's boundaries respond to changes in solar wind pressure across the ascending phase of the cycle. Comparing IMAP's maps with Voyager's in-place measurements creates a combined dataset of unprecedented richness. One probe looking at the boundary from the inside, while 2 others report from the outside. But the probes on the outside are fading. The fragility of the Voyager spacecraft became terrifyingly clear in late 2023. On November 14th, Voyager 1 stopped making sense. The spacecraft continued transmitting. Its radio signal still arrived at the Deep Space Network antennas on Earth at the expected intervals and at the expected frequency. But the data inside the signal was wrong. Instead of readable science and engineering telemetry, Voyager 1 was sending a repeating pattern of 1s and 0s that contained no usable information. The stream was not random noise. It was structured, orderly, and completely meaningless. The spacecraft was talking, but it was speaking gibberish. Engineers at the Jet Propulsion Laboratory began troubleshooting immediately, but immediately on a spacecraft 24 billion kilometers away means something different than it does on Earth. Every diagnostic command sent to Voyager 1 took more than 22 hours to arrive. Every response took another 22 hours to return. A single question and answer exchange consumed nearly 2 full days. Diagnosing a problem that a technician in a laboratory could investigate in minutes required weeks of patient, methodical remote interrogation across the longest communication link ever maintained with a functioning machine. By March of 2024, engineers had isolated the source, a single memory chip in the flight data subsystem, the computer responsible for packaging science and engineering data before transmission, had failed. The chip contained a portion of the software code that the subsystem needed to format its output correctly. With that code corrupted, the subsystem could still operate, but everything it produced was garbled. The spacecraft's other systems, its attitude control, its power management, its communications transmitter, were all functioning normally. Voyager 1 was healthy in every other respect. It simply could not tell anyone about it. The fix was extraordinary. Engineers could not replace the chip. They could not upload new hardware. They could not reboot into a backup system that did not exist. They had to reroute the affected software, moving the corrupted code to other locations in the flight data subsystem's remaining functional memory, a memory architecture designed in the early 1970s and never intended to be reconfigured in flight nearly half a century later. The process required identifying which portions of memory were still usable, rewriting the code to function from its new location, transmitting the revised instructions across billions of miles of empty space, and waiting to see whether the reformatted subsystem would resume producing intelligible output. On April 20th, 2024, engineers sent the first set of rerouted code. More than 22 hours later, Voyager 1 responded with readable engineering data for the first time in 5 months. The spacecraft was talking again. Over the following weeks, the team restored science data from 2 instruments, then 2 more, until by mid-2024, all 4 instruments that were still powered on at that time had resumed returning usable measurements. The interstellar medium data that had gone dark for 5 months began flowing again, and the gap in the record was the longest interruption since launch. The recovery was celebrated, but it left a scar on the mission's confidence. The flight data subsystem contains other aging components. The memory is old, the processors are old, the software was written for hardware that no longer exists in any laboratory on Earth. Every chip, every transistor, every solder joint aboard Voyager 1 has been operating in the radiation environment of deep space for nearly 5 decades, enduring temperature cycles, cosmic ray strikes, and the slow degradation that accompanies being very far from maintenance for a very long time. The 2023 anomaly was not a freak event. It was a preview of the spacecraft's inevitable decline. It demonstrated that a single failed component in one subsystem can render the entire data stream useless for months. The next failure might be recoverable, or it might not. Engineers cannot predict which chip will fail next, or when, or whether a workaround will be possible within the dwindling power and memory budget. The spacecraft is not merely old, it is operating at the outer boundary of recoverable failure, where every anomaly becomes a race against distance, power, and the irreversible mathematics of decay. In February of 2025, engineers at the Jet Propulsion Laboratory sent commands to Voyager 1 to shut down its cosmic ray subsystem. This was the instrument that had helped confirm the heliopause crossing in 2012 by recording the dramatic surge in galactic cosmic ray intensity. It had been operating nearly continuously since launch in 1977, almost 48 years. Turning it off was not an emergency decision. Years earlier, the Voyager science and engineering teams had agreed on a prioritized shutdown sequence, a carefully ordered list dictating which instruments would be sacrificed and in what order as power continued to decline. The cosmic ray subsystem was next on the list. In April of 2026, the low-energy charged particles instrument followed. This detector, which had measured energetic ions and electrons throughout the heliosphere and into interstellar space, was turned off on April 17th. It had operated for nearly 49 years. The instrument had provided critical measurements of the heliosheath's particle environment, detected pressure fronts in the very local interstellar medium, and contributed to density estimates in regions where no other instrument could sample. Its data will be analysed for years after its shutdown. As of mid-2026, Voyager 1 operates with only 2 science instruments still powered on, the magnetometer and the plasma wave subsystem. That is all. Out of 10 original instruments, 8 are now silent. The spacecraft's radioisotope thermoelectric generators produce barely enough electricity to run those 2 detectors, the communication system, and the heaters that keep critical components above their minimum operating temperatures. Every year, the generators lose roughly 4 more watts. The margin between operation and silence narrows with each passing month. Engineers are not surrendering passively. In 2026, The Voyager team is preparing a last resort power-saving maneuver they have internally nicknamed the Big Bang. The plan is to swap out multiple powered components simultaneously, replacing some with lower power alternatives and switching others off entirely, all in a coordinated sequence designed to wring the maximum possible operational lifetime from the remaining electrical budget. Voyager 2, which retains slightly more power than its twin and is closer to Earth, making communication faster, is serving as the test subject. Trials were planned for May and June of 2026. If those tests succeed, the same procedure will be attempted on Voyager 1 no sooner than July. If it works, there is even a possibility that the low-energy charged particles instrument could be switched back on, at least temporarily. But every intervention on a spacecraft this old and this distant carries risk. If something goes wrong during the Big Bang procedure, the round-trip communication delay means engineers will not know about it for nearly 2 full days. And they will have to diagnose the problem, design a fix, transmit the repair commands, and wait another 2 days to learn whether the fix worked. All while the spacecraft continues moving farther away, its signal growing fainter, its power continuing to drop. There is no backup. There is no second chance. There is no spacecraft behind Voyager 1 that can take over its measurements if it falls silent. The loneliness of this situation is difficult to overstate. Voyager 1 is the most distant functioning machine humanity has ever built. In November of 2026, it will cross a milestone that has nothing to do with plasma physics or magnetic fields. On November 18th, a radio signal travelling at the speed of light will require a full 24 hours to reach the spacecraft. 1 complete light day. The distance is approximately 25.5 billion kilometers. No human object has ever been this far from home. No human signal has ever travelled this long to reach a working receiver. And yet Voyager 1 has not left the solar system. Not by the broadest, most physically meaningful definition. It crossed the heliopause. It exited the sun's plasma bubble. It entered the interstellar medium. But the sun's gravity has not released it. The sun's gravitational influence extends vastly beyond the heliosphere, reaching outward to the theoretical Oort cloud, the spherical reservoir of icy bodies that marks the true gravitational boundary of the solar system. The inner edge of the Oort cloud may begin somewhere between 1,000 and 2,000 astronomical units from the Sun. The outer edge may extend to 100,000 astronomical units, approximately 1.5 light years. Voyager 1, at roughly 170 astronomical units, has crossed less than 0.2% of the distance to the Sun's gravitational boundary. It will not reach even the nearest estimated inner edge of the Oort cloud for over 200 years. It will not exit the Sun's gravitational domain for approximately 30,000 years. By the time Voyager leaves the solar system in the gravitational sense, human civilization will either have transformed beyond recognition or cease to exist entirely. This is the distinction that the heliopause crossing revealed with painful clarity. Interstellar space and the solar system overlap. They are not the same boundary. Voyager 1 is simultaneously in interstellar space, surrounded by galactic plasma and galactic cosmic rays, and deep inside the solar system, firmly bound by the sun's gravity, closer to our star than to any other. The heliosphere is not the solar system. It is one feature of the solar system, the sun's plasma bubble, nested inside a vastly larger gravitational structure that extends more than 1,000 times farther. The edge Voyager crossed was real. The boundary exists. The solar wind does stop. Interstellar plasma does begin. But the crossing did not mark an exit. It marked a transition from one kind of solar influence to another, from the sun's magnetic and plasma dominance to the sun's gravitational dominance alone. Voyager traded one form of the sun's reach for a quieter, subtler, and far more expansive one. And even that gravitational reach eventually ends. Somewhere past the outermost fringes of the Oort cloud, the sun's gravity finally becomes too weak to hold anything in orbit. Beyond that point, objects drift free, belonging to no star, answering to no sun. That true edge lies so far away that Voyager's instruments will have been dead for millennia before the spacecraft reaches it. What awaits at those distances, and what it means for everything Voyager has already measured, is the last question worth asking. There is a question that no spacecraft has ever answered, and no spacecraft currently flying ever will. What does the heliosphere look like from the outside? We know the boundary exists. Voyager proved that. We know it has layers. We know it is porous. We know the solar wind stops and the interstellar medium begins. But we have never seen the shape of our own bubble. Every model of the heliosphere, every animation in every documentary, every diagram in every textbook is a guess. An educated, mathematically rigorous, physically motivated guess, but a guess nonetheless. No camera has ever been far enough away and pointed back at the sun from the right angle to photograph the structure that protects everything we have ever known. We are inside the bubble, and from inside, you cannot see the shape of the thing that surrounds you. This is not a trivial problem. The shape of the heliosphere determines how effectively it shields the inner solar system from galactic cosmic rays. A long, streamlined shape with a thick nose and an extended tail would provide substantial protection in the forward direction and along the flanks. A shorter, squatter shape might leave certain angles more exposed. The shape also determines how the boundary interacts with changes in the interstellar medium as the sun moves through different regions of the galaxy over millions of years. If the sun passes through a denser pocket of interstellar gas, the heliosphere compresses. If the local density drops, it expands. The degree to which the bubble inflates or contracts in different directions depends on its geometry, and its geometry depends on physics we can model but have never directly confirmed. For decades, the standard picture was a comet-like shape, a blunt, rounded nose pointing into the interstellar wind, a gradually widening body swept back along the flanks, and a long, narrow tail extending downwind for hundreds or thousands of astronomical units. This shape emerges naturally from magneto-hydrodynamic simulations that treat the solar wind as a fluid, interacting with an oncoming interstellar flow. The nose compresses because the interstellar medium rams against the heliosphere head-on. The tail stretches because the deflected solar wind has nowhere to go but backward, forming an elongated wake. The analogy to a comet's shape, with a rounded head and a streaming tail, became the default illustration in nearly every popular representation of the heliosphere. Then Mehrav Ofer challenged it. In a series of papers beginning in 2015, Ofer, an astrophysicist at Boston University, proposed a radically different geometry. Her models incorporated the sun's magnetic field in a way that earlier simulations had simplified. The sun's magnetic field is not uniform. It has two polarities, north and south, separated by a wavy current sheet that extends outward through the heliosphere. Ofer's simulations showed that these two magnetic hemispheres, when they reach the outer heliosphere, do not merge smoothly into a single tail. Instead, they separate into two distinct lobes, forced apart by magnetic pressure, creating a shape that Ofer described as a deflated croissant. Two fat, rounded jets of magnetized solar wind material extend downwind of the sun, separated by a gap where interstellar material can push inward between them. If Ofer's model is correct, the heliosphere is not streamlined, it is split. The two lobes create a structure that is wider and shorter than the classical comet picture, with interstellar plasma able to penetrate much closer to the sun along the gap between the jets than the comet model allows. This geometry would change estimates of cosmic ray shielding in the tail direction, and would alter predictions for how the heliosphere responds to changes in interstellar conditions. The debate remains unresolved. Other groups have produced simulations that support a more traditional elongated tail. Some hybrid models suggest the truth lies somewhere between the two extremes, with the heliosphere occasionally reshaping itself as solar activity fluctuates. The heliosphere is not a rigid structure. It is more like a candle flame in a drafty room, its shape responding in real time to changes in the wind from both inside and outside. The solar cycle inflates and deflates the bubble every 11 years. Coronal mass ejections create transient bulges. Variations in the local interstellar medium alter the external pressure. The heliosphere's shape at any given moment is the product of all these competing forces, and it may never hold a single stable geometry for long. IMAP's higher resolution energetic neutral atom maps may help settle the question. By tracking how the boundary responds to solar activity across multiple years, IMAP could reveal whether the tail region splits into two lobes, as Ofer predicts, or remains a single coherent stream. The mission's pickup ion measurements will also probe the three-dimensional distribution of interstellar material flowing through the heliosphere, providing constraints on the shape that no previous dataset could offer. But even IMAP maps the boundary from inside. The definitive answer, the actual external photograph, remains beyond our reach. What we do know is that our bubble is not unique. The Sun is not the only star that blows a wind into space. Nearly every star with a hot outer atmosphere generates some form of stellar outflow, and that outflow creates a bubble wherever it meets the surrounding interstellar medium. Astronomers call these structures astrospheres, and a handful have been directly observed around nearby stars. The most striking example is Lil Oriohanes, a young star in the Orion Nebula. The Hubble Space Telescope photographed LL Orionis' astrosphere in stunning detail, capturing the bow shock where the star's powerful wind collides with the dense gas of the surrounding nebula. The image shows a bright, curved arc of compressed material wrapping around the star's windward side, with a fainter, elongated wake trailing behind. It is, from the outside, a photograph of what the heliosphere might look like if we could step far enough away to see it whole. Other astrospheres have been detected in different ways. Astronomers have identified absorption signatures in the spectra of nearby stars that indicate the presence of hydrogen walls, dense pileups of neutral hydrogen at the boundary between a stellar wind and the interstellar medium. The Sun has its own hydrogen wall, predicted by models and partially confirmed by Voyager's ultraviolet spectrometer data. These walls form because interstellar hydrogen atoms are slowed and compressed as they approach the astrosphere's edge. The universality of astrospheres carries profound implications. Every star that generates a wind creates a protective cocoon around its planetary system. The strength and extent of that cocoon depend on the wind's power, which in turn depends on the star's mass, age, rotation rate, and magnetic activity. Young, rapidly rotating stars blow fierce winds that inflate large, robust astrospheres. Old, quiet stars produce weaker winds and smaller bubbles. Red dwarfs, the most common type of star in the galaxy, often have intense but variable magnetic activity that may create astrospheres very different in character from the Sun's heliosphere. The degree of cosmic ray shielding that a planet receives depends critically on the astrosphere its star maintains. This means that habitability is not just about a planet's distance from its star, not just about liquid water and atmospheric composition. It is also about whether the star provides an adequate magnetic shield against the galactic radiation environment. A planet in the habitable zone of a star with a weak or absent wind would be bathed in galactic cosmic rays at a level far higher than anything Earth experiences. The biological consequences could be severe: increased mutation rates, cellular damage, constraints on the complexity of surface life. The timescales involved sharpen the point. Life on Earth required roughly 3.5 billion years to progress, from the first single-celled organisms to the complex multicellular ecosystems that exist today. That long, unbroken evolutionary arc depended on conditions remaining broadly stable across geological time. A planet whose cosmic ray environment fluctuated drastically every few million years because its star's wind was erratic or its astrosphere was undersized, might never accumulate the biological complexity that Earth achieved. Mutations drive evolution, but too many mutations too quickly overwhelm repair mechanisms and destroy genetic integrity. The heliosphere provided a radiation ceiling under which Earth's biology could innovate slowly, fail safely, and build complexity without being periodically sterilized by galactic particle bombardment. This connection between stellar winds and biological evolution is a relatively new idea in astrobiology. For decades, habitability assessments focused almost exclusively on the surface conditions of planets themselves: the right temperature, the right atmospheric pressure, the right chemistry. The stellar environment beyond the planet's magnetosphere was treated as background, constant and unremarkable. Voyager's measurements at the heliosphere's edge helped change that perspective by demonstrating that the boundary is real, that it fluctuates, and that the shielding it provides is neither uniform nor guaranteed. The Voyager data gave astrobiologists a new variable to consider. When we evaluate whether a planet orbiting a distant star could harbour life, we now ask not just whether the planet is in the habitable zone, but whether the star maintains a stable astrosphere large enough and strong enough to keep galactic radiation at manageable levels over billions of years. Some stars almost certainly do. Others almost certainly do not. And for the majority in between, the The answer depends on magnetic properties and wind strengths that we are only beginning to measure from Earth. The heliosphere is not merely an interesting feature of the solar system. It may be one of the reasons complex life was able to evolve here at all. And understanding it, through the data Voyager gathered at its edge, informs every assessment we make about the prospects for life around other stars. Voyager has proven the concept. The boundary exists. The shield works. But Voyager also demonstrated the limits of what two spacecraft can reveal. Two crossing points on a three-dimensional boundary, spanning tens of billions of miles in every direction. Two sets of measurements at two locations during two specific moments in the solar cycle. The heliosphere is dynamic, asymmetric, and responsive to conditions that change over years and decades. To truly understand it, future missions will need to go farther, go faster, and carry instruments designed specifically for the boundary environment, not instruments repurposed from a planetary flyby mission nearly 50 years old. NASA recognizes this gap. In 2021, the Johns Hopkins Applied Physics Laboratory completed a comprehensive study of a mission concept called the Interstellar Probe. The goal was ambitious: send a spacecraft to roughly 1,000 astronomical units from the Sun within a 50-year mission lifetime, crossing the heliosphere's boundary and traveling deep enough into the interstellar medium to sample truly undisturbed conditions far from the Sun's influence. To reach that distance in a human career span, the probe would need to travel significantly faster than either Voyager. The study examined a technique called a solar Obert maneuver, in which the spacecraft would first dive close to the Sun, then fire its engines at closest approach, exploiting the Sun's deep gravity well to achieve an enormous velocity boost on departure. Combined with a large launch vehicle, this technique could accelerate the probe to speeds several times Voyager's current velocity. The speed requirement is non-negotiable. Voyager 1 travels at roughly 17 kilometers per second and took 35 years to reach the heliopause. To reach 1,000 astronomical units within a 50-year mission, a spacecraft would need to sustain an average outbound velocity of roughly 95 kilometers per second, more than 5 times Voyager's speed. The solar Obert maneuver achieves this by exploiting a counterintuitive principle of orbital mechanics. A rocket engine produces the same thrust regardless of how fast the spacecraft is already moving, but the kinetic energy gained from that thrust increases with velocity. By diving deep into the Sun's gravity well, the spacecraft accelerates to enormous speed under solar gravity before even firing its engine. When the engine fires at closest approach, where velocity is highest, the energy gain from the burn is maximized. The spacecraft then climbs out of the gravity well on a hyperbolic trajectory, retaining far more speed than any conventional launch could provide. The engineering challenges are severe. At closest approach, the spacecraft would pass within a few solar radii of the Sun's surface, enduring temperatures that would melt conventional materials. It would require a heat shield comparable in concept to the one used by the Parker Solar Probe, but engineered for a much faster transit. The burn at closest approach would need to be precisely timed, because even a few seconds of error at those velocities translates into significant trajectory deviations at interstellar distances, and the spacecraft would need to survive for 50 years in the interstellar medium with no possibility of repair, carrying instruments sensitive enough to measure densities of a few hundredths of a particle per cubic centimeter and magnetic fields weaker than a 10 millionth of the strength of a refrigerator magnet. None of these challenges is beyond current engineering capability. The Parker Solar Probe has already demonstrated close solar passes. Radioisotope power systems have sustained spacecraft for decades. Deep space communication networks can maintain contact at distances well beyond 1,000 astronomical units with planned antenna upgrades. The Interstellar Probe is not a fantasy. It is a mission waiting for a decision. The Interstellar Probe would carry instruments designed for the boundary region, including cameras capable of looking back at the heliosphere from outside and capturing, for the first time, an image of the Sun's bubble as a whole. It would cross the heliopause in less than 15 years rather than the 35 years Voyager 1 required. End quote. It would pass through the hydrogen wall, the pile-up of neutral atoms at the heliosphere's outer edge, and measure its density and structure directly. And it would travel far enough into the interstellar medium to sample conditions beyond the disturbed zone that still affects Voyager's measurements. reaching the pristine galactic environment that Voyager may never live to see. The interstellar probe remains a concept study. It is not yet a funded mission. It has no launch date. It exists as a set of engineering analyses, trajectory designs, and scientific justifications, waiting for the political and budgetary conditions that would allow it to proceed. Whether humanity sends an interstellar probe in the next decade, the next century, or not at all, depends on decisions that have nothing to do with physics and everything to do with will. In the meantime, the only instruments measuring interstellar space remain the fading detectors aboard 2 spacecraft launched when the personal computer did not yet exist. And those instruments are dying. Voyager 1's radioisotope thermoelectric generators now produce roughly enough electricity to power 2 household light bulbs. And from that entire budget must run every heater, computer, transmitter, and science instrument still operating aboard the spacecraft. The thermocouples that convert plutonium heat into electricity have degraded steadily alongside the slow decay of the fuel itself. Each year, roughly 4 more watts disappear from the dwindling electrical budget. The spacecraft has already shut down 8 of its 10 original instruments. 2 remain. The magnetometer, which tracks the direction and strength of the surrounding magnetic field, and the plasma wave subsystem, which detects electron oscillations in the local plasma. Together, these 2 sensors provide the last thread of scientific data connecting humanity to the interstellar medium. When the power drops below the threshold needed to operate even these instruments and maintain the communications link, Voyager 1 will fall silent. Engineers estimate that could happen sometime in the late 2020s or early 2030s, depending on how successfully the remaining power-saving measures extend operations. If the Big Bang procedure works, it might buy additional months or years. If it fails, or if a fault protection event triggers an unrecoverable configuration, the end could come sooner. No one can predict the exact date. What is certain is that the silence is coming. After nearly half a century of continuous conversation with Earth, Voyager 1 will send its last intelligible signal, and the deep space antennas that have been listening since 1977 will hear nothing in return. When that happens, the physical spacecraft will not stop. It will continue traveling at roughly 17 kilometers per second, coasting on the momentum it accumulated from planetary gravity assists decades ago. No engine is firing, no course correction is possible. Voyager 1 will drift through the very local interstellar medium, then through the broader interstellar space of the Sun's galactic neighborhood, carrying with it a golden record, a 12-inch gold-plated copper disc encoded with sounds and images from Earth, selected by a committee chaired by Carl Sagan in 1977. The record contains greetings in 55 languages, samples of music from cultures around the world, natural sounds of wind and surf and birdsong, and 116 images of life on Earth. It was designed as a message to any intelligence that might someday encounter the spacecraft. The odds of that encounter are, by any honest reckoning, essentially 0. Interstellar space is so vast and so empty that Voyager could drift for billions of years without approaching another star closely enough for any hypothetical civilization to detect it. In approximately 40,000 years, Voyager 1 will pass within roughly 1.6 light-years of a faint red dwarf star called Gliese 445 in the constellation Cumel O Pardulis. It will not enter that star's planetary system if one exists. It will simply glide past, a silent, powerless artifact, carrying a record no one will play, bearing a message no one will read, representing a species that may no longer exist by the time the encounter occurs. The golden record was never really for aliens. It was for us. It was a way of saying that we were here, that we built something, that we sent it outward carrying the best of what we are. The record does not make Voyager's journey meaningful. The data does. And the data tells a story that changes what it means to live on this planet. Before Voyager, the solar system was a set of orbits, planets circling a star in an orderly arrangement, surrounded by empty space, bounded by nothing in particular. The edge was wherever the last planet was, or wherever Pluto was, or wherever you decided to stop drawing the diagram. There was no physical structure marking the boundary, no membrane, no wall, no shield. The sun gave light and warmth, and beyond the sun's light, there was simply the void. Voyager revealed that this picture is fundamentally incomplete. The sun does not merely shine, it exhales. It fills the surrounding space with a continuous supersonic outflow of magnetized plasma that inflates a bubble extending more than 100 astronomical units in every direction. That bubble holds back the interstellar medium, a cold, dense, magnetically threaded plasma that would otherwise flood the inner solar system with galactic cosmic radiation at levels significantly higher than what Earth currently experiences. The heliosphere is not decoration, it is infrastructure. It is the invisible architecture that makes the inner solar system a place where complex molecules can persist, where DNA can replicate without being shredded by radiation, where biology has a chance. We did not know this until we sent a machine to the edge and watched what happened when it crossed. The termination shock, the heliosheath, the heliopause, these were theoretical constructs until Voyager flew through them and reported what the instruments measured. The magnetic field that refused to rotate, the plasma density that jumped by a factor of 40, the cosmic ray intensity that surged as the sun's shield fell away behind. These were not predictions fulfilled. They were surprises. The boundary was messier, thicker, more porous, and more dynamic than any model had anticipated. The interstellar medium was hotter and more disturbed than expected. The sun's influence reached beyond its own boundary, distorting the galactic magnetic field for tens of astronomical units past the heliopause. Nothing about the edge was simple, nothing about it was clean, and that is the discovery. Not that the edge exists, not that interstellar space is far away, not that Voyager is brave or lonely or poetic. The discovery is that the sun has been protecting us inside an invisible boundary that we could not see, could not detect from Earth, could not photograph, and could only understand by building a machine, launching it into the darkness, and waiting 35 years for it to reach a wall we were not entirely sure was there. The heliosphere is a shelter we never knew we lived inside, and we only learned about it because we sent something almost beyond the reach of communication to find it. Voyager 1 is now more than 170 astronomical units from the sun. A radio signal from Earth takes nearly 23 hours to reach it. A reply takes another 23 hours to return. The round-trip conversation time approaches 2 full days, and yet the sun's gravity still holds it. The sun's gravitational influence will not release Voyager for roughly 30,000 years. The spacecraft crossed the edge of the sun's plasma domain, but it remains deep inside the sun's gravitational embrace, closer to our star than to any other, bound by an invisible tether that extends far beyond anything the solar wind could reach. Somewhere out there, long after the last instrument has gone dark and the last watt of electrical power has faded to nothing, Voyager 1 will continue drifting. It will carry the golden record through the interstellar medium at 17 kilometers per second, a velocity that sounds fast, but covers only 1 light year every 18,000 years. The spacecraft will not reach the distance of the nearest known star system for tens of millennia. It will move through space that is cold, thin, magnetically threaded, and utterly indifferent to its presence. No force will slow it significantly. No object will intercept it. It will simply coast, a small metallic object barely larger than a compact car, growing colder as its plutonium slowly spends its warmth, its antenna still pointed at a sun it can no longer see. If you could somehow stand on Voyager 1's antenna platform and look back the way it came, the sun would still be visible. At 170 astronomical units, our star would appear roughly 30,000 times fainter than it does from Earth, but it would still be the brightest point in the sky, a sharp, brilliant pinprick outshining every other star by a wide margin. It would no longer warm anything. Its light would carry no useful energy at that distance, but it would be there, unmistakable, the anchor of a planetary system that Voyager left behind decades ago but has not yet escaped. Ahead of the spacecraft, in the direction of travel, there would be nothing distinguishable. No landmark, no brightening, no sign that anything awaits. The constellation Ku-Mel-O-Pa-Da-Li, toward which Voyager 1 is heading, would look exactly the same as it does from Earth. The stars are so distant that Voyager's entire journey since launch has not shifted their apparent positions by a measurable amount. From the spacecraft's perspective, it has been travelling for nearly 50 years and has not moved at all. The sky is identical. The stars are unchanged. only the sun behind it has dimmed. This is the loneliness of interstellar travel at the speeds available to current technology. Voyager moves at 17 kilometers per second, roughly 38,000 miles per hour, fast enough to cross the entire United States in 5 minutes. Yet at this velocity, it will be 40,000 years before it even passes near another star, and that passage will miss by more than a light year. The interstellar medium offers no markers, no milestones, no indication of progress. There is only the signal growing fainter, the power declining, the instrument shutting down one by one, and the sun slowly losing its distinction among the stars until, thousands of years from now, it fades into the undifferentiated glow of the Milky Way. By then, Voyager will carry no working instrument and produce no signal. It will be the farthest object humanity has ever placed in the universe, and no one will know exactly where it is. The last coordinates will be the ones calculated from the final tracking data, projected forward using orbital mechanics, growing less precise with every passing century. Voyager will become a ghost, a mathematical estimate drifting through an ocean that has no shore. From the sun's perspective, Voyager is a grain of metal vanishing into the darkness between the stars, carrying a fading whisper that will soon fall silent. From humanity's perspective, it is the farthest thing we have ever touched, the longest conversation we have ever sustained, and the most profound measurement we have ever made. It found the edge. It crossed the edge, and it showed us that the edge is not a wall or a line or a border. It is a turbulent, layered, breathing membrane where our star's last breath meets the galaxy's first, and where the protection we never knew we had slowly gives way to an environment that does not know we exist. The sun is still shielding us. Right now, as you hear these words, the solar wind is blowing outward, past every planet, past every comet, past the Kuiper belt, pushing against the interstellar medium, inflating the bubble that has sheltered life on Earth for 4.5 billion years. The heliosphere is holding, the cosmic rays are being turned away, the boundary is intact. But Voyager showed us what waits on the other side. Not hostility, not malice, just indifference. A thin, cold, magnetized medium that stretches between the stars for light years in every direction, that does not care what it touches, that has been there since before the sun ignited, and that will remain long after the sun burns out and the heliosphere collapses for the last time. Voyager drifts outward, alone, its instruments dimming, its signal fading, a tiny warm object growing colder in a silence that has no edge of its own.